Okay, we're going to review kinematics problems using this Google Spreadsheet. And you'll be doing a couple sets of problems similar to this, where you analyze the data in tables and graphs. So let's assume we have a rock falling freely from rest for 6 seconds, and it accelerates at 10 meters per second per second. First, complete the data table, and then we're going to graph both relationships, velocity versus time and the displacement versus time. So in the first table, you have 6 seconds of time. So we'll start at time 0, 1, 2, 3, 4, 5, 6. And you can repeat that for the second table. Okay. The problem says that it falls freely from rest. So you know the initial velocity at time 0 is 0. And then it accelerates at 10 meters per second, which means every second it increases its velocity by 10 meters per second. So you can kind of figure this out. But if you want to look at one of your kinematic equations, you might recall that final velocity equals initial velocity plus acceleration times time. Substitute the initial velocity for 0, the acceleration rate for 10, and you simply get that the velocity is 10t. So 10 times 1 is 10, 10 times 2 is 20, 10 times 3 is 30, and you see the pattern. Velocity increases by 10 meters per second each second, in line with the problem and using the right equation below. We'll do the same for the next data table. This one's a little trickier because you want to know the displacement of the rock. How far did it fall after 0 seconds? 0 meters. After 1 second, after 2 seconds, what is the vertical displacement as it's falling? Now, it does accelerate down, and displacement could be down in the negative direction, but we're just going to keep it, these are positive values for now. If you use the kinematic equation, d equals VIT plus half AT squared, VI is 0, acceleration is 10, substitute your givens, and you simply get half the acceleration is 5t squared. So all you have to do is substitute your time into this equation, square it, and then multiply it by 5. So if you do that, you'll get 5 meters. When time is 2, you should get 20 meters. When time is 3, 45 meters. When time is 4, 4 squared is 16 times 5 is 80 meters. When time is 5, 5 squared is 25 times 5 is 125 meters. And 36 times 5 is 180 meters. So this rock will fall 180 meters after 6 seconds. Now, if you look at the data, which of these trends looks linear? You can tell by looking at the pattern. Every 1 second interval of time, the velocity increases by 10 meters per second, the same amount each unit time. But the distance does not. The distance increases by an increasing amount each second. It keeps getting larger and larger and larger because it's accelerating. So you won't get a linear relationship for distance versus time, but you will for velocity versus time. So we're going to highlight this data, highlight all the data starting at cell A4, click and drag to cell B11, insert into a chart. When you get your chart editor, you get a little chart editor that appears. The default setting is a line chart, but you want to move to the right and choose scatter. The scatter chart always displays the ordered pairs of data as points. And then you can determine if a line is the best fit, and it looks to be a linear relationship. These points all appear collinear. So if you go to Customize, go to the right, Customize, Series, expand that menu, and as you scroll down, you have a box for trend line. And if you check that box, the default setting says linear, and a linear trend line appears to be the best fit because it touches all the points. scroll down a little further, and you can use label none, but we want to change that to use equation. Close the chart editor, and you will see there's an equation that's in slope-intercept form, mx plus b. You have a slope of 10 times x plus 0, and intercept is 0. And that equation, if you look carefully, let's just click and drag and drop this below our data table. Let's drop it below like row 16 so you can kind of compare. We use this equation, velocity equals initial velocity plus acceleration times time. So in that equation, the acceleration rate was 10, and the initial velocity was 0. You can see a similarity with the linear trendline equation. So the slope 10 here is the acceleration, 10x plus 0, and 0 was the initial velocity. So anytime you graph a velocity versus time graph, and you see a linear trend in the data, and to make this easier, what we can do is we can simply select the 3 little dots in the top right corner. You can move to its own sheet. And then we can go back to sheet 1, which has the data, makes it a little easier. Velocities is graphed on the y-axis, time in units of seconds on the x-axis. We have a nice title, velocity versus time. We have an equation that models the trend line. And it's a linear fit showing that the velocity is increasing at the same amount each second. It goes up by 10 meters per second each second between every successive point. Okay, so now you know how to do a linear trend line for a set of data that you've plotted as x, y ordered pairs. Every time you use a spreadsheet, you always put the x data first, that's the time, and the y data second, which was the velocity. And we'll do the same here. Time will be the x data, the displacement will be the y data. And we're going to highlight this just the same. Highlight all ordered pairs from cell D4, click and drag to cell E11, insert into the chart. And when you set this up, once again, the default chose scatter instead of line, which was good. We want scatter. Okay. Now, when you customize, again, we're going to choose, we should have the chart titled already. The axes are already labeled, so we're just going to select series like we did before. And we're going to check the box for trend line. Now you see linear is the default setting, but if you look at the graph does not appear to be linear. These data points don't increase by the same amount each second. They kind of curve. They have the slope is increasing. So we're going to change that to polynomial. And once you make the change, you notice that the curve touches every point. So this is the model that fits the data. It's not a linear model. It's a polynomial. In fact, it's a quadratic, degree 2. That's why it says degree 2, second degree. Some people, when you study quadratic equations, you've heard that the graphs are called parabolas. And you can close this out. We won't label this with an equation because it doesn't have a slope-intercept form where the slope has meaning. But you can tell by looking at the slope, it's changing between every 2 points. It appears to be getting steeper and steeper and steeper, so the slope is increasing. And if you remember, the slope of a distance time graph represents the velocity. So the velocity is getting faster and faster because the object is accelerating. Once again, we're going to select the 3 dots in the top right corner. You can move this to its own sheet, makes it a little easier to see. Your x-axis is labeled time in seconds. Your y-axis is the distance or displacement. In meters, you have a title. And you can clearly see it's not linear. You have a quadratic fit, this little parabola curve that shows an increasing slope each second. Okay, so what we have done is we have modeled the data trend in two different tables for a rock in free fall for 6 seconds, accelerating due to gravity at 10 meters per second squared. We're going to do the same for sheet number 2. So on the bottom, you have a sheet number 1 with charts, 2 charts. Scroll to sheet number 2, and there's a new problem. Okay, this problem says a ball is thrown up at 40 meters per second. So now we have an initial velocity. It's thrown up vertically. It reaches its highest point in 4 seconds, then stops momentarily because at that instant at the top, the velocity is 0. And then the ball falls back down. Okay. You're going to complete the data tables below and then graph both relationships. Assume that the acceleration rate due to gravity is negative 10 meters per second always. Remember, you can't turn gravity off. It's always causing the ball to change its velocity by negative 10 meters per second each second throughout its upward motion and downward motion. And now the negative sign is important here because it means something. It means it's slowing down as it rises and it's speeding up in the negative direction as it falls. So if you throw it up and it reaches its highest point in 4 seconds, it comes back down in 4 seconds. So we will have 8 seconds of time. Let's fill out that column first. Okay. Do it again. Okay, we got the time filled out. Now we have to calculate the velocity at each second. Initially, the velocity is 40 meters per second, and then it changes by negative 10 meters per second. So it's not increasing, it's actually decreasing because when you throw it up, it's slowing down. So it's changing by negative 10 meters per second each second, which means it goes from 40 to 30 to 20 to 10 to 0. So you can see after 4 seconds, it now has a velocity of 0. That's at the highest point. And then the ball turns around and comes back down, so it starts to speed up in the negative direction to negative 10, negative 20, negative 30, and finally negative 40 meters per second. That's a rate of change of negative 10 meters per second each second. And if you model that with an equation, final velocity equals initial velocity plus acceleration times time. The initial velocity was 40 meters per second. The acceleration was a negative 10. So you're just simply saying 40 minus 10t. And if you plug in those t values, you can calculate the velocity at every second. In spreadsheets, we use the asterisk, shift 8, to represent multiplying. So that asterisk is always multiplication. We don't use the x for multiplication because it looks like a variable. All right, we know the velocity at every second throughout its flight. Now what about the displacement? Okay, this is a little trickier. Well, at time 0, it hasn't moved yet. But once you throw it up, you know the distance it travels is equal to the initial velocity times time plus half the acceleration rate times time squared. So if you substitute your givens, you get 40t plus negative 5t squared. Just depends on what time interval. So we have to plug in all 8 seconds here for t and solve for d. Substitute your t values, solve for d, and put it in the table. And what you should find out is that once you toss this object up into the air, after 1 second, it travels about 35 meters. That's 40 plus negative 5. After 2 seconds of time, that's 80 plus negative 20. You get 60 meters of displacement, so it's getting higher, but not quite as fast. And then 75 meters. After 4 seconds, you will get 80 meters. It's peak height, from which its velocity slows down to 0 and it turns around. And as it falls back down at the same rate it was rising, just in the opposite direction. So now it's back to 75 meters above the ground. 60 meters above the ground.